In this unit, we will be looking at the law of mass action for combined reactions. Sometimes we know the equilibrium constant for two separate reactions, but we need to find the equilibrium constant of the overall reaction. And we're going to talk about the mathematical manipulations we can use to figure out the K value, or the equilibrium constant, for that overall reaction. We are going to determine the effect of manipulating an equation on the equilibrium constant of a reaction. The first thing we can see is that when we reverse the reaction, we invert the equilibrium expression. So if we look at the equilibrium expression, or the law of mass action, for our first reaction, what we see is K for 1 equals C cubed over A times B squared. And we get this from the stoichiometry of our balanced chemical equation, because we have a coefficient of 1, 2, and 3. If I reverse the reaction, I see a slightly different K value, and I see K minus 1 indicating the reverse reaction, and I have AB squared over C cubed. Now mathematically, this is just the inverse of what we saw for K1. So if I want to find the equilibrium constant for this reverse process, all I have to do is take the inverse, or K to the minus 1, of the equilibrium constant for the first reaction. If I multiply the coefficients by some factor, we actually raise the equilibrium constant to that same power. So for example, if we write the law of mass action for our first reaction here, we have the same thing we did before, K1 equals C cubed over AB squared. When I look at twice that reaction, I say 2A plus 4B yields 6C. I've just multiplied everything by 2. When I look at K2, I get C to the 6th over A squared B to the 4th, because I have different coefficients, so I have to put those in there. But when I look at the relationship between K2 and K1, I see that K2 could also be written as C cubed over AB squared, with the entire expression squared, and that would be the same as K1 squared. So if I multiply a reaction by some factor, I can simply raise the K value to that power. Remembering what we know about our mathematical relationships with powers, that x squared squared is equal to x to the 4th, x to the 6th is equal to x to the 3rd to the 2nd power. When we add reactions, we have to take the product of those two K values. So if I take A plus B yields C, I can write my law of mass action, so my K1 value there. When I look at B plus D yields E, I can write K2, so E over B and D. Now if I add those two reactions, I end up with A plus 2B plus D as my reactant side, and end up with C and E on my product side. So now if I write the K3, if I write the equilibrium expression for that overall reaction, I get C times E over AB squared D. If I look at K1 and K2, I see that this is simply the product of those equilibrium expressions, because I can break that down into each part, and as a result, I can find the equilibrium constant of K3 by simply multiplying K1 times K2. So let's look at an example here. How are K1 and K2 related to K3? What is the relationship between these first two terms that will get me to my K3 value? Hopefully you got B for the answer, because when we look at our reaction, we see that reaction 3 is simply the sum of reaction 1 and reaction 2. Here we have A plus 2A, so that gives us 3A. We have 2B and 2B. We see that we have a C on the product side, but we also have a C on the reactant side, so they're not in the overall reaction. They cancel out. And on the product side, I have 2D and 2D. So since my overall reaction, the third reaction, is simply the sum of reactions 1 and 2, the value of K3 will be equal to K1 times K2. In the next unit, we'll look at the relationship between Kp and Kc. Kp is the equilibrium constant with respect to pressure, and Kc is the equilibrium constant with respect to the concentrations.